So far, all of the equations that we have solved have had a single trig function in them. So that it has been one equation with sine in it in one place, or cosine in it in one place, or something like that. So that's going to stop as of now. We're going to have equations where we have multiple trig functions in them, or equations where sine of x might show up in a couple of different places, that kind of thing. So trig identities are going to help us with that. They're also going to help us simplify trig expressions, and we actually use existing trig identities to prove new trig identities, and that is a brand new skill. Okay, so this first example is one we're not actually going to solve. It's just an example of why we need these trig identities. So if you look at this first equation, this equation says that sine divided by cosine is equal to the square root of 3. And that means it's got two different trig functions in it. So we could not just use inverse trig to solve it. But there's a trig identity that you guys have known for about 6 weeks now that said that tangent of x was equal to sine over cosine. So that means that we are allowed to take that original equation that says sine divided by cosine is equal to square root of 3 and replace it with tangent of x is equal to square root of 3. And that would allow us to solve it, finally. So that's what we call a quotient identity, and they were given to you in the notes about alternate definitions of trig about 6 weeks ago now. And so I just want to refresh your memory on those. Tangent of theta was defined back then to be sine of theta divided by cosine of theta, which you may remember more because on the unit circle we called it y over x, which is what that is, sine over cosine. And if tangent is sine over cosine, then cotangent is cosine over sine. Secant is the reciprocal of cosine, so secant is 1 over cosine, and therefore cosecant is 1 over sine. Okay? The other set of identities that are incredibly important throughout multiple units in trig are called the Pythagorean identities, and they come from the Pythagorean theorem, hence the name for them. And so what it says here at this spot on the notes is it says jump over to trig identity activity number 1, which you picked up with these notes. And so I want you guys to take a moment and flip to that trig identity activity. And steps 1 through 6 are asking you to recreate the circle that I did for the first several days of notes. You may remember that we started out, as soon as we hit angles of rotation, we started drawing circles with the x and y axis through them. And I kept making triangles into the first quadrant. And for a long time, those triangles had random numbers for the adjacent side, which was x, and the opposite side, which was y, and we called this r. And it's asking you to recreate it inside the unit circle, and so those didn't stay random numbers. So I want to see if you guys can quickly recreate that picture I've already drawn question 1 and 2 for you. I want you to do 3 through 6. So pause the video and see if you can recreate the point where it hits the circle and the sides of the triangle. Okay, so hopefully you paused the video like I asked you to, and what you should have hopefully come up with is that the point where our angle hits the unit circle, like it said, the x-coordinate is cosine and the y-coordinate is sine. And that's because you're inside the unit circle, which means the hypotenuse is 1. And this side that was just a random x-coordinate is no longer random. It's now cosine. And this side is sine. And so that's what you would have filled in the blanks on number 5 and 6. The side opposite from the angle got labeled sine of the angle, and the side adjacent to the angle got labeled as the cosine value for the angle. Now the reason that you needed to do that is because the Pythagorean theorem, as you were taught it, is just a squared plus b squared equals c squared. But in this right triangle, a, b, and c have new names. And so step 8 and 9 are going to talk about doing that substitution step and what you come up with once you've done that substitution step. So if I took that a squared plus b squared equals c squared inside of the right triangle up at the top of the page, one of the legs has now been renamed as sine, and it's going to get squared, so it becomes sine squared of x. The other leg is cosine, and so it's going to get squared, and so it becomes cosine squared of x. And the hypotenuse is 1, and when it gets squared, it stays 1. Okay? And what we've just derived, or come up with, is the first Pythagorean identity. So I'm going to flip back a couple of slides and look at the actual front side of the notes, because that first Pythagorean identity is this one right here, and it says that sine squared of one angle plus cosine squared of the same angle, it's always going to be equal to 1. So the one thing that you've got to really understand, though, is when we say that you're going to have to memorize these identities, first of all, don't panic. There's a blank underneath this that says the only 2 sets of identities you will have to memorize all year are the quotient, which are these up here, and the Pythagorean. In any of the other units we're going to do that have identities in them, we will give you the identities. Or if it's a formula or just a regular formula to use, we'll give you the formula. And I also want to make sure you know there are only 2 more trig units to go after this current one. So I know trig has been rough, but it won't last that much longer. But we do need to make sure you understand that when we say memorize the Pythagorean relationships, we don't just mean that you need to know sine squared plus cosine squared is 1. You need to recognize it when it's been rearranged. You need to be able to mentally manipulate it for yourselves, just in your head. For example, this first Pythagorean identity, I could take sine squared and move it to the other side of the identity, and the identity would become this. And that's it. I mean, that's still the first Pythagorean identity, but I need to be able to recognize that, because it's going to be very important when we use it to substitute for other things, that it's not always going to be in just one form of it. Okay? So the other 2 Pythagorean identities come from the first one. So what step 10 asks you to do is it says take sine squared plus cosine squared equals 1. And divide the whole thing through by cosine squared. And see what you come up with. Now remember, I don't want to keep flashing back and forth to the different slides, but remember that tangent was sine over cosine. So that means that sine squared divided by cosine squared would be tangent squared. Cosine squared divided by itself would be 1. And 1 divided by cosine was secant. So 1 divided by cosine squared would be secant squared of x. And so that is the second Pythagorean identity. It comes from the first one by doing a single division step to it. So then step 11 would ask you to repeat that process and see what you come up with. So I want you guys to try that one for yourselves. You don't have to pause it or anything. I'm just going to wait a few seconds. And I may even write down the beginning of the problem while you guys work. So just see if you can come up with the final identity for yourselves. Okay, I don't want to make the recording any longer than it's already going to be, so I'm You can pause it if you don't want me to go ahead and work through the rest of the problem for you and take a second. But this identity is going to work out to where you do sine squared divided by itself and you get 1, plus cosine squared divided by sine squared is cotangent squared, and 1 divided by sine squared is cosecant squared. And that is the third Pythagorean identity. So if you only memorize one of them, obviously the first one would be the most important because you can derive the other two from it. But I would recommend you memorize all 3 of these Pythagorean identities and learn to rearrange them and that kind of stuff in your head. Now the reason we need these identities is because they're going to allow us to do 3 new skills. They're going to allow us to solve equations we couldn't previously have solved. They're going to allow to prove trig identities that haven't been proven yet, and it's going to allow us to simplify a variety of things along the way. So if you look at this new equation on method 1, we're going to use our quotient identities, and we can use our quotient identities whether we're solving, proving, or simplifying. So we're combining the different methods with the different uses. This equation has 3 different trig functions in it, which means as of right now we would not have been able to solve it. But if I use my quotient identities, then that means that I can replace secant with 1 over cosine of x. Sine doesn't have a replacement, it just stays sine of x. And I'm going to write it over 1 because it's going to be multiplied to tangent, and tangent's going to get rewritten as a fraction. It's going to get rewritten as sine of x over cosine of x. Now, I've temporarily made the equation look messier, but now I actually have some operations I could do. PEMDAS would actually have something that it would allow me to do, and it would allow me to multiply these 2 things together, and then it would allow me to actually subtract, which before I couldn't have done. So I'm going to go ahead and I'm going to follow PEMDAS now. First, I'm going to multiply the 2 fractions together. So I multiply straight across. Sine of x times sine of x is sine squared of x, and 1 times cosine is cosine of x. So I did the multiplying step of PEMDAS. Then PEMDAS says that I would do my adding and subtracting. Fortunately, these 2 fractions already have a common denominator, so I can subtract. So I go ahead and I subtract them, and I have 1 minus sine squared of x over the common denominator, cosine of x, equals 1/2. And if you'll flash back just a minute or 2 ago, I reminded you guys that you need to recognize your Pythagorean identities in all their different rearranged forms. 1 minus sine squared was what I had rearranged that first Pythagorean identity to look like. And 1 minus sine squared is equal to cosine squared, which means I can replace it. And the reason I want to replace it, I'm going to replace my numerator with cosine squared. And the reason for that is because now the fraction reduces. I've got 2 cosines being multiplied on top. I've got a cosine on bottom. So this cosine would cancel with one of those. And I am left with a very simplified equation that just says cosine of x is equal to 1/2. Okay? And now I actually have the ability to solve it. So here was the domain we were solving this equation over. It said between 0 degrees and 360 degrees. So remember that technically the step I'm doing is inverse cosine, but I'm really just answering the question, what angles have a cosine value of 1/2? And the 2 angles between 0 and 360 degrees that have a cosine value of 1/2 are 60 degrees and 300 degrees. So an equation that I previously would not have been able to solve, I was able to rewrite it and simplify it, and then I was able to solve it. Okay. The second method involves using Pythagorean identities before you resort to your quotient identities. Your quotient identities are what we call your fail-safe identities. They will almost always, fail-safe identities. almost always get you where you want to go, but odds are if you resort to them every time, it's going to take you a lot more steps and it's going to make it a lot messier than it needs to be. Okay, so I could use my quotient identities here like I just did in the first problem, but it means I'd put a fraction here, a squared fraction here as part of a binomial, and then a fraction here, and it would become a hideous mess. So I am not going to resort to my quotient identities first. I'm going to use my Pythagorean identities first, and then resort to my quotient identities. So for the sake of space, I'm going to have to do a little erasing here. You can always rewind or just look at the website. It's got the completed notes on there too. Okay. And what I'm going to do is this section is going to get replaced with the Pythagorean identity. Before I start, there's a couple of rules about doing proofs. The first and most important rule about doing a proof is that you cannot manipulate both sides. Okay? And people are used to being able to do things to both sides because they're used to being given equations that look like this, where you already know that x plus 4 is equal to 7, and so it's safe to do the same thing to both sides. The problem with a proof is that you don't know that. You are trying to prove that these two things, this thing and this thing, are equal to each other. And if you don't know that they are equal to each other, you cannot move things around both sides and continue to treat them like they're equal to each other. That's not true. So now, rule number one with a proof, you have to work with one side only and prove it becomes the other side. You don't do anything to both sides. Okay? The second rule is that, or the general rule, is that you want to start with the sloppiest side, the hardest side, and prove it simplifies to the other side. It's a lot easier to go from the messy to the simpler than the other direction. Okay? So that's what I'm going to do. In order to show the person who's reading the proof what side I'm starting on, I need to write it down. So I'm actually going to rewrite the side that I am starting with. So this is the side I'm choosing to start with. It's the messy side. I'm going to prove it becomes the simpler side. Okay? So I'm going to use my Pythagorean identity first. The second Pythagorean identity is going to allow me to replace that binomial right there. 1 plus tangent squared is going to get replaced with secant squared. Because that is an identity. We already know that to be true, and we know those things to be equal. Okay? Now I can resort to my quotients, and it doesn't seem like I've saved myself a ton of work, but I have, because I no longer have a binomial here, and that's going to make a huge difference. I will not have to do common denominators. I will not have to turn things into a single term. Okay? So it actually does save me about 4 steps of work to do it this way. So now I use my quotients. I replace cotangent with cosine over sine. I replace secant squared with 1 over cosine squared. And I replace tangent with sine over cosine. Okay? And I know that it seems like a horrible mess, but look at what you really have. If you really think about what you have a fraction here times a fraction here, and then you're dividing by this fraction down here. So I can do a rewriting step. I don't need to leave it written as dividing by a fraction. So I'm going to erase to make room, because I think that's easier. I want to keep track of what I've done and what I'm looking at, so I don't want to flip to a blank screen. So I'm going to do a rewriting step. I have cosine of A over sine of A times 1 over cosine squared of A. But instead of leaving this down here written as division, I'm going to turn it into multiplying by its reciprocal. Cosine A over sine A. And now, stuff starts canceling like crazy. If you look at what you are doing in this proof, you have this cosine here times this cosine here, but you have 2 cosines down here already. So these 2 are going to cancel with those 2. All 4 cosines just canceled out of there. And that leaves nothing but 1 on top. And then on bottom you have sine of A times sine of A, which is sine squared of A. And then you're actually at your endpoint, because 1 over sine squared of A is the definition for cosecant squared of A. Check. We're done. We proved it became what it was supposed to become. Okay? And that's how you do a proof. And we are going to do lots and lots of practice with it. Monday is going to be a catch-up day and a practice day. And I promise you we will give you as much help as you guys need and as I can come up with. Okay? And then method 3 is algebraic methods. It's actually a very broad method. It's anything algebra related. So you could factor and reduce. You might have to rationalize a fraction. You might have to give common denominators, things like that. And so we're going to have to refresh some of your algebra skills. And so this is a very, very broad set of problems. So I'm going to do 1 proof and 2 simplifying. I actually like the proofs better than the simplifying, because with the proof I know what it's supposed to become. I know when I've reached the end. With the simplifying problem you don't necessarily know that. So I look at this proof right here, and I'm going to start with the left side again, because remember you typically want to start with the messy side. Both sides are fractions. Makes people want to do crazy things like cross multiply, but remember on a proof you can't use both sides. I'm going to use the left side because it's got a binomial in the denominator. Automatically makes it messier. So I start with that side. Guess I'm going to start here. And I rewrite it so that I know the person who's reading it knows where I started. And the first method listed under the algebra skills is rationalizing. And remember, rationalizing means getting rid of something you don't want in the denominator. And we do that by multiplying by the conjugates. Now, conjugates is probably a term you haven't heard us use yet this year, but if I asked you what is the conjugate of x plus 3, its conjugate would be x minus 3. And the reason that they're conjugates is because they are binomials that are identical except for the sign in between the 2 terms. And conjugates do special things with each other. Stuff starts canceling out, which is our goal. And so we're going to talk a lot more about conjugates both in this unit and the next unit, and then again next semester in some of our other units. But the conjugate of 1 plus sine theta would just be 1 minus sine theta. And so I'm going to multiply by 1 minus sine of theta both on the top and the bottom. Okay, it's just like rationalizing another fraction where you just have a radical in the denominator. If I wanted to rationalize this, remember, I would have to multiply by square root of 3 on top and on bottom. Okay, because remember this is numerically equivalent to 1. So I'm not actually changing anything's value. So that's what I'm doing, is I'm rationalizing to get rid of the sign in the denominator. And I'm doing it with the conjugate, and I'm doing the same thing on top and bottom. Okay? Now when I do that, and this just takes practice, I'm actually not going to distribute through the top. I'm going to leave the numerator written in factored form. And hopefully you'll see why after enough practice with this. Okay, leave the numerator written that way. Also keep in mind, I know what I'm trying to make this become, so I know I want a 1 minus sine of theta on top eventually. But I am actually going to FOIL out my denominators. And because these are conjugates, watch what will happen. First terms give me 1. Outer terms give me minus sine of theta. And inner terms give me plus sine of theta. And the last terms give me minus sine squared of theta. So the outer and inner terms cancel. It's one of the perks of using conjugates. And what I'm left with is both of the factors up in my numerator. And in the denominator, all I'm left with is 1 minus sine squared, which you may or may not recognize because we've seen it twice now already. 1 minus sine squared can get replaced with cosine squared. That's that rearranged first Pythagorean identity. And then I'm almost done because the cosine that's up here will cancel with one of the cosines that's down here, and I've reached my goal. I have proven that my messy fraction can also become equal to this fraction. And that's it, we're done. Okay? So that's just another example of a proof, and we did it with rationalizing. Okay? The second problem in this third method, we're going to use that common denominator method because it was listed second in the list of algebraic methods. And this time, unfortunately, we're doing a simplifying problem, which means we don't actually know when we are done. That just takes practice. You'll know when you've taken it far enough. And we'll talk about how we know that once we get to the end of this. Okay, so I'm going to give these two things a common denominator. Okay, so I'm going to multiply the first fraction by cosine over cosine. And I'm going to multiply the second fraction by sine over sine. Okay, and I'm going to be adding these two fractions together, so ultimately, unfortunately, I don't have a choice. I have to distribute when I multiply, or I won't have anything that are like terms that I can combine. So I'm going to distribute the cosine through that numerator, and so it will become cosine of theta plus cosine of theta times sine of theta over the common denominator, which is now cosine of theta times sine of theta. Okay, and then I take this and I distribute through here. And if you can mentally visualize this, it'll save you a step of writing, and you can see these are long steps to write out. Remember that cotangent is cosine over sine. So when I do sine to the cotangent and they multiply together, the sines would cancel, and this would just become cosine. And then distribute there, and I get minus cosine times sine over the common denominator. Okay. So you can see it's long and it's messy, but the messiest part of it is about to cancel out of there, because when I add these two fractions together, let me change colors so it'll stand out. When I add these two fractions together, this term and this term are opposites of each other, so when they add, they will cancel out. So on my next step, when I add these two fractions, all I will have is cosine of theta plus cosine of theta, which would be 2. Cosine of theta over the common denominator, which is cosine of theta sine of theta. And then I have a 2 times a cosine on top, and I have a cosine times a sine on bottom, so the cosines would cancel, and I would have 2 over sine of theta. And if 1 over sine is cosecant, then 2 over sine is 2 cosecant of theta. So I think it's really cool because we went from this horrible mess right there to just 2 cosecant. That's it. Can you imagine if I was mean enough to make this into an equation you had to solve? It'd be a whole lot easier to solve now than it was originally. And that's why I think trig proofs are cool and trig simplifying is cool, because to watch stuff that's so messy become so simple is just awesome. So, and I guess that's why I'm a math teacher. I'm not sure you guys enjoy it like I do. But we have one question left, and it's actually the easiest of the bunch, so I'm sure you're tired of listening to me. But our last method's going to be factoring. That's what I'm going to do to this problem, is I'm going to factor it and reduce it, and that's it. I will be simplified. And don't think that things are always going to simplify down until they're pretty. Sometimes it just doesn't become pretty, but it becomes prettier than it started out. So my numerator factors because it's a difference of 2 squares. This is a perfect square minus a perfect square. Sine squared would split up as sine and sine. And the 1 splits up as 1 and 1, but one of them's a plus and one of them's a minus. It's that special quadratic factoring pattern. And I love all things quadratic. So there are quadratics written into your trig units, there's quadratics written into your exponential units, there's quadratics written in as quartics into your polynomial unit. You're going to see them all year long because I love quadratics. And then the denominator factors, because it's got a greatest common factor. Both terms in the denominator have tangent in them. When I pull that tangent out, it leaves a sine of theta in the first term and a -1 on the second term. And those are factors that would cancel. Now, believe it or not, we're done. Because this actually doesn't become much simpler. You can leave it like that. If you want to take it farther, you could. But it's a fraction with a single term in the denominator. And so there were a variety of ways you could split it up. You could continue to rewrite it. But they may or may not actually make it look simpler. For example, you could rewrite this as sine over cosine. And so if you did that, then you would be dividing by a fraction, which means then the next thing you could do is you could turn it into multiplying by the reciprocal. And then this would have to distribute through here. And so when I distributed to the first term, the signs would cancel again, and I would just have cosine. And when I distributed to the 1, I would just have cotangent. So you see how different those two versions of an answer look. And neither one of them is particularly pretty. It really, a lot of the times, is a matter of personal choice. Or you'll be given a variety of options as to what it could simplify to, and you're going to need to find one of the potential correct answers. Okay, so there's a lot of ambiguity about when are you finally at your end point. Okay, so that will just, once again, take practice. So I know these notes are long enough. I'm sorry for those of you who are absent. Be assured that Monday is going to be a practice and catch-up day. Monday, those of you who are absent, you can take your trig inverses quiz in class, or you can come in before school or during lunch or something and take it, and we'll get you guys caught up. Take care.